So just a moment before we are preparing the slide. Okay. Okay, the second speaker is Tina, and her talk is titled Language Politeness in Social Networks.
Thank you very much. So, in this talk, I will talk about language politeness in the framework of game theory and the theory of social networks. So, first of all, the two examples we have seen a lot in this topic. The first one is pass me the thought example. So these two sentences have the same intention, but the second one phrased in a question style and in a bit longer sentence. So depending on the different effects, you may phrase it in a much more indirect way, as the second example shows. So it's about borrow money. So we have seen this different kind of indirectness in the use of politeness. So from the point of view of information transaction, maybe it's not a complete model to explain this notification. So one of the most influential model for this LP is the Brown-Levinson's face-threatening model. So they think from the speaker's point of view, they want to give some room for the opponent to reject their request. So politeness is kind of mitigate or avoid this kind of face threatening for the request. And we also discuss about the different level of politeness, and the degree could be divided by the three kinds of parameters: the social distance, power difference, and the inclination rate by different requests. So we call this as a strategic view. Language politeness because from your benefits of the individual benefits. And along this line of discussion, there are several game models already constructed. So I listed some of them, but it's like all of the current work I can find. Maybe there are some, but these are really discussions. So actually, there are not so many. Okay. Then, and an alternative way, there is a conventional view about LP, especially in some cross-cultural studies, and they think language is more of a relation technology devices rather than a strategic behavior. And one of the typical example is in Japanese culture, and they think people to act properly because they want to keep their relative positional rank with regard to their position in the society or community. So this is a typical example in Japanese saying today from a very impolite to a very polite way. But they explain this kind of politeness not as a strategic point of view, but as a conventional custom in the Japanese language. So my idea is to add in this social network structure, which can kind of combine these two views. So first view is a strategic view. We care about the distance and the power difference within the network. So for example, in the left graph, the speaker consider the distance between the two hearers and they use different phrases, the level of politeness. And in the second graph, the hearer too apparently has many more neighbors than the tier one. So in the tier of a social network, the number of neighbors is kind of index of a person's centrality in this network, also index of the powerful. So we can see these two elements can be expressed formally in a social network theory. So additionally, we can also use this social network to express the conventional meaning of a sentence, which means when speakers talk with the hearer, he wants to be consistent with the hearer's neighbors. So want to be as close as to how other people are talking with something talking. So actually, this theory, there are many discussions about this conventional view from Zoe scheme, and also combine this signal again with the social network assumption. So idea of a paper is to starting with a very simple communication game from this paper. Then I add this social network structure. Then I add some repeated play and dynamic to this model and show some simulation results. Then some expected results are the following two. So we expect to answer how different social structures affect the degree of LP and how different models like strategic, conventional, or conventional two are affected by different social networks. So the following are focus on this. So the following would be more technical details about the game model, and I would focus on the structure of the model and the simulation results. So first of all, let's look at the basic game I adapt from this paper, which describe a very general phenomena when someone raises a request to another guy. So R represents the rate of integration of a request. Then P is presented as a level of different classes. Then PH, the capital PH, is a response function from the hearer's point of view, depends on the integration rate and the specific tightness to receive from the speaker. Then the expected utility is calculated by the request times the realized response function and minus the cost of the slightness. So two comments about this model. Firstly, this model is purely from the speaker's perspective, so the hearer's incentive is not clearly specified, like why I'm going to help you if I don't have any benefits from this model. So this topic is not clearly defined in this book. So I'm going to add a little bit more constraint about this assumption. The second is I will add this social network thing into the model. So this is a new model. So first, the players are located in the network. So N represents the set of players. Then E is a connection between the players I and G. So at each time, if the connection is one, so they are connected. Then I and J are played in twice. Once I is asking for a request, the other times the hero asks a request. So this is essential for why the hero would like to respond positively, because in the future he would become the speaker and ask for a request. Then he wants to get a positive response. Okay, the next definition is about the social distance. So the social distance has two parts. The first, small d, that's the distance in the network between two people. So we use the shortest distance. The capital N, that represents the neighbor, the number of neighbors of the hill. So with these elements, we characterize the power difference of the hill. Then 4 is we define the inclination by the crest as a function other than a constant. So it's a function from this social distance and the rate. And this function could change in our repeating scan later. So I will show the detail how this changes in the dynamic model. So 5, 6 are the fixed action. It's the same as before. And the utilities defined clearly as before. So the original model also made the following assumptions about the utility functions. So the first assumption says the utility function is monotonously increasing the increase of the cycle. And the cost function is also increased as the increase of the degree of cycle. So there are some empirical work to support this assumption. So the following is as an example of the utility function, which satisfies with assumption 1 and assumption 2. So this is not unique, just for the simplified calculation. So we make this utility functions. And according to the utility function, we can solve for the capital P, so the maximum politeness for this function, giving the F. So F is the social integration here, which in this function we treat it as a constant, but we define it in a function in a separate. So this is a graph to show the utility function. So the EUS is the utility function giving different social integration S. So S0, S1, and S2. And the linear function is a cost function, and the utility is one minus the other. So the red part is the utility. As we can see, so S0, S1, and S2 is decreasing, so getting smaller. So as S getting smaller, the utility is increasing. So that's the dynamic of the connections. So in the dynamic model, I will show how the S changes from 0 to 1, 1 to 2, and which should fit into the picture of decreasing and increase utility. Okay, now I will talk about how this can work in a social network in a repeated style. So the first one is the punishment. So this rule is actually essential to define why the healer would like to accept this request or respond positively to the speaker's request. So if an agent rejects agent I request, then agent I has a positive ability to reject case request in the future. So this gives the hearer incentive to claim this request. So in the simulation, we will consider 2 versions. So the basic version is the always positive response. The second version is randomly. So there is a probability that the speaker would get a rejection. And we assume that this rejection rate increase as their distance getting bigger. So to ask someone stranger for a request, you are highly possible to be get rejected. So this is also the assumption we made in the simulation. And the second rule we made is about the change of the social information. So this rule says that the repetition communication decreases the social rate of imposition for fixed request and fixed solution distance. So it's like if I made a request to the same person and I got a successful result, there are more possible to ask the same guy for the same kind of request. So this is how this dynamic roles intuition is. So the change of the F, so the social information is a function of the distance and the rate of the information caused by the request is updated according to the utility. So the basic idea is the higher utility gives you less social information. So if you last time you get more benefits from this communication, then next time it's easier to ask the same thing. So that's the same kind of basic idea. So it's implemented in this math formula. So the first one is only considered a strategic view. So the second part, we can consider a new dynamic, which includes the conventional point of view, which is the blue part. So this is the conventional part. It's just the take the average of the neighbors of the peers social integration. Every time you update your own social integration. So social integration is the important indicator of the politeness. Then omega is just a parameter to balance these two things. Okay, so this is how FP changes in the dynamic later. So we do 4 simulations according to our different assumptions. So we consider 2 kinds of dynamic. Dynamic 1 only consider the strategic view, and dynamic 2 consider both. And we have 2 versions for this period response. One is always positive response. Then the other is there's a possibility to reverse. So according to this combination, I did 4 simulations. And I used the following 3 social structure to run this simulation. Then why do I choose these 3 networks? So the most right one is the complete, which means everybody has full connection with everyone else in this network. So it's equal for each one in this network. And another extreme case is the middle one, the star shape, where one player has the most connection with every other, but other people don't have direct connections with all the rest. So it's kind of 2 extreme cases. And the green one is kind of in the middle, which is for comparison for the simulation. So the simulation will show for each simulation how the 3 networks in a different level of politeness. And also I show by fixing a 30 network how these different simulation like models are different. So first this is the result because there's a time limit. So these 3 are the main observations. So when we consider the long distance communication cost, which is reflected in the punishment flow. So long distance communication gives you higher rejection rate. So first, if you don't consider this cost, then the star-shaped network has the least average tightness, and the complete network has the highest tightness. And the ring-wise in the middle, then 2 is the average. If we consider the cost, then the result is turnaround. And the 3 is showing how these 4 models are different by fixing certain networks. Okay, so this is the first one, comparative results. So we show that 1, 2 is long communication cost, then the brightness is complete is the highest. Then 3 and 4 if we consider this random response. The second is, sorry, I need to repeat. So when we fix certain network, then how different simulations result differently. Then we can see that in the complete network, these lines almost have the same shape. So the complete network is less sensitive to all these different dynamics. So next few slides are just to, if we change the parameter a little bit, how the model results changing. For example, the response rate difference, and how this omit difference resulting in the distribution of different solutions. So last slide. So future works. So first one, because we add the series response as the exogenously dual to the model. But more interesting ways to see how this intensive behavior can be induced from the model itself. So the idea is to add some connection strength into the network, and by the connection strength, then he would like to attack. Okay, something like this. The second one is a bit more complex network. The third one is another big problem and empirical data to support. So this is a little bit difficult. Okay, thank you very much.
Okay, we have 8-ish minutes for discussion. So there's a question from Zoom, so let's take that. Susan, can you ask a question then?
Yeah. Can you hear me?
Yes.
Thank you for your talk. I have a question. The main difference, technical difference, yourself between yourself, your model and Muhlenberg's model is to introduce social distance function, social distance, main difference.
There
Technical
are
difference.
two main differences. First of all, of course, to introduce the social network, like you said, the social distance. The second one is the repeated play of the game.
Yeah.
Yeah.
So what instead of introducing social distance, Muhlenberg's model, Muhlenberg's model in place of social distance, in place of social distance, Muhlenberg's model, what kind of concepts introduce Muhlenberg's model? What kind of in place of social distance?
You mean why use the social distance?
Yeah. social distance is your main concept, and what is the Muehlenband's game theoretic model? What is the main idea of Muehlenband's model? Your main idea is social distance, and on the other hand,
Social distance idea is not from me. So in Brown electric model, they already mentioned social distance is one parameter decides the level of correctness. So I just implemented in a theory of social network so that we can do kind of like formal characterizations of the politeness.
yeah. Thank you. Thank you.
Thank you. Thank you.
Okay, thank you very much. Any other question? Go ahead.
Yeah, thanks. That's very interesting. I wanted to ask kind of about how do your models allow like uncertainty about the social status of the different people?
It's kind of this, yeah, there's some.
Because I guess I was feeling like, once you have uncertainty about social status, there's going to be lots of very surprising effects related kind of to the punishment principle. So like one kind of dynamic I was thinking is like, well, maybe I'll reject the person's request, but that'll actually, opposite of the punishment principle, that'll make them more likely to help me, because if they don't know my social status, then by my rejecting the request, that'll increase, they'll think I'm a higher social status because only a high status person would reject a request. And then they'll be more likely to do what I want in the future. And I would think that dynamic gets even stronger in social network settings, because then even if the person who I asked is less likely to help me in the future, everyone watching will think, okay, they have high social status, so I'll listen to them in the future,
Exactly. So the one of the main reasons I like this kind of simulation models, you can play around with it. It's like you have this intuition of a probability makes you more possible to request. So you just like write code to verify what would happen if you make this extra assumption. But I think more importantly is, do you have like real data to support your simulation results? You can do many kinds of things, but where do you want to go?
Yeah.
Yeah.
I just wanted to throw out a similar uncertainty dynamic I was thinking involving the language of politeness is sometimes there's an incentive to be ruder instead of polite to signal that you're higher status when there's uncertainty about your status. Whereas if there was total certainty about status, it seems like the dominant thing would be to be polite,
Exactly, but in model, I don't have this like social status so much, but yeah, you're correct, because I focus on the probability part only on the social distance. The physical distance.
I guess I would think
but
that
you can see that the power part would play the role of this.
I was kind of thinking the probability, maybe the probability of answering requests is kind of like status, and then you could have uncertainty about what the chance is that the person will answer requests.
Put the probability on a probability.
Yeah.
That's possible. Yeah, you need to have a like intuitive idea to support it. Yeah, if it makes sense, why not? You can try. Thank you very much.
Okay, thank you. Which was first? There are two questions. Then Sumio Nishiguchi-san, can you ask a question?
Yeah, thank you for the talk. I have a question about the social distance between the speaker and the hearer. Technically, could there be a maximum number of small n, the number of the neighbors?
N is the distance. So sorry. So the capital N is the number of neighbors of player J within the N distance. So the small n means the distance. You can have many neighbors with, you can including the neighbors with 10 different powers from, but we may consider this like you only count the number of neighbors within one distance only.
I see. And is there any proportion? Is there any proportion between D and N, Dij and Njn? Like, does the number of neighbors contribute a lot, and does it drastically change the? What's the proportion between?
So currently, I treat them like equally because I don't have a parameter between the smaller d and the capital N in this. Yeah, you can put some parameter weights for like you care more about the neighbors or you care less about the physical distance. So that's also possible to implement.
Thanks.
Thank you.
Okay, thank you. So unfortunately, I think we are running out of time. So, I mean, could you ask questions in chat or maybe later?
Thank you
Speaker
very
again.
much.
Thank you.